Hello students, in this video we'll discuss multiple linear regression. In this setup we have a target variable y, which we seek to explain as beta 0 plus beta 1 times a predictor x1 plus beta 2 times a predictor x2 all the way up to beta p times a predictor xp plus epsilon. And epsilon, just as in simple linear regression, is normally distributed with mean 0 and variance sigma squared. So that's what the epsilon, that's what the error term is. The irreducible error term is normally distributed. Now, we're in the context of a vector situation, and what we can do is we can write this. We can write each individual observation over here. For example, I can write y1 as beta 0 plus beta 1, and then x11 plus beta 2, x12 plus beta p, x1p plus epsilon 1. And then etc. down over here. We can write yk, the kth observation, as beta 0 plus beta 1 xk1 plus beta 2 xk2 plus beta p xkp plus epsilon k. So we can write down our observations this way. And we can write this as, instead of writing down this massive equation, we can write this as a vector equation. If we let x be this design matrix, so what will the design matrix be? The design matrix is going to be a whole bunch of 1s down over here. So 1, 1. There's going to be k1s, and then there's going to be an x11, x1p, all the way down to xk1, xkp. So let's check to see what we have over here. So we have the number of rows. We have our k rows. So I have k rows, and I have p plus 1 columns. So this is a k by p plus 1 matrix. And what I can do with x is I can form a vector beta, which is this column vector. It'll be beta 0, beta 1, all the way down to beta p. So this over here, so this matrix over here, this matrix x is k by p plus 1. And this is a p plus 1 by 1, p plus 1 by 1 column vector. So I can actually form xb. So using this notation, I can say that the vector y, my vector y, is equal to the matrix x, this design matrix, times beta plus the vector epsilon over here. So this is my relationship I have over here. And so from this we can see what the expected value of y is. The expected value of y, of the vector y, is going to be, well, this is, epsilon is normally distributed with mean 0, so this is just going to be x beta. That's the expected value of y. So this y vector is itself normally distributed. Y is normal with mean x transpose x, just x beta, comma, that's the mean, and the variance of y is just going to be sigma squared. Okay, excellent. And so now the question for us is, how can I find an estimate for the betas? So that's our question. The question of MLR, multiple linear regression, is how do we estimate right? How do we estimate these coefficients beta? And the answer to that is we're going to form this equation over here. We're going to answer, we're going to minimize the sum of square errors. What do I mean by that? I'm going to consider this equation over here. I want to minimize over all coefficients b0, b1, bp. I want to find the minimum of the sum. We have, remember, we have k observations over here, so I'm going to go, j goes from 1 to k of y, that's going to be a yj. So yj, not k of course, yj, yj, minus beta 0. And then I'm going to look at the jth observation. So I'm going to have a beta 1 xj1 minus all the way down to beta p xjp quantity squared. Now, of course, what we're really doing over here is we're doing this expression, we're minimizing the sum of squares. It's easier to write this minimization down in terms of a norm problem. So this is exactly the same thing as saying this is the minimum over all b0, b1, bp of doing what? Of doing y minus x b, the vector b. Oh, so these are going to be b's now. So we want the b's instead of the betas. So these are going to turn into b's because the betas are the actual parameters in the problem. So we want b's over here. We want b0 minus b1 x1 minus bp xp. B transpose y minus x b, which is exactly the same as minimizing over b0, b1, bp, the length of y minus x b squared. And so now we see that if the vector y is in the column space of the matrix X, then I can perfectly minimize this and make this equal to 0. In general, though, y will not be in the column space of the matrix X. So what we'll do is we'll consider what the estimate's going to be. The estimate y hat will be the projection of y onto the column space of X. And the b vector will exactly be the element in the column space that corresponds to that estimate. We'll see that in a future video. Thank you very much.